This video prepared to show basic of spontaneous potential, that also called self-potential. Spontaneous potential is a naturally occurring electric potential difference in the Earth, measured by an electrode relative to a fixed reference electrode. Spontaneous potentials are often measured down boreholes for formation evaluation in the oil and gas industry, and they can also be measured along the Earth's surface for mineral exploration of groundwater investigation. The phenomenon and its application to geology was first recognized by Konrad Schlumberger, Marcel Schlumberger, and E.G. Leonardon in 1931, and the first published examples were from Russian oil fields. Spontaneous potentials, one of the earliest laws used and still in use, primarily used for determining gross lithology, a reservoir versus non-reservoir, permeable versus non-permeable, used as correlation logs, several other equally important use.
A record of direct voltage that develops naturally, spontaneous between a movable electrode in a well and a fixed electrode located at the surface, measured in millivolts. A spare response created by electric voltages arising from electrochemical factors in a borehole and adjacent rocks. Spare readings are caused by differences in salinities between mud filtrate and formation waters in permeable beds. Salinity of a fluid is inversely proportional to its resistivity, so in practice mud filtrate salinity is indicated by mud filtrate resistivity and formation water salinity by formation water resistivity. Conductive light necessary in borehole to create a spare response, so a spare cannot be used in non-conductive drilling muds or in air-filled holes. Usually displayed in the left track correlation, used to detect permeable beds, detect boundaries of permeable beds, determine formation water resistivity, determine the volume of the shale in permeable beds, detection of hydrocarbons by the suppression of the SP curve. As we see on this sim, the SP is located on the left track and it well fitted with the other correlation on the sim. Static spontaneous potential, maximum SP that a thick, shale-free, porous and permeable formation can have for a given radio between RMF and RV, determined by formula or by chart, necessary for determining accurate values of RV and volume of shale. SP influenced by bed thickness, bed resistivity, borehole diameter, invasion, shale content, hydrocarbon content, and most important, radio of RMF and RV. On this part of our presentation, we want you to know the terms of the SP. First is SSP, max deflection possible for given RMF or RW. SP response due to presence of zinc beds or gas presence. PSP, pseudostatic SP when shale is present.
What influences SP measurement? Bed thickness. Thin formations, the measured SP is less than the SSP. Narrow, pointed SP curve. Correction for bed thickness required. Bed resistivity. Higher resistivities reduce the reflection of the SP curve. Borehole and invasion, usually very small and can in general be ignored. Shale content, presence of shale in a permeable formation, reduces the SP deflection. Hydrocarbon content. In hydrocarbon bearing zones, the SP curves deflection is reduced. Hydrocarbon suppression only qualitative, not possible to determine SHC. Shale baseline. Shale baseline, the relatively constant SP response of shales, assumed to be zero. Permeable zones indicate where there is a deflection from the shale baseline. SP readings are measured relative to the shale baseline, can drift over long distances, of little consequence for single formations.
Shape of the SP curve. Shape and amplitude of the SP deflection opposite a permeable bed depends on thickness, H, and true resistivity, RT, of the permeable bed. Resistivity, or Rx0, and diameter, d, of the zone contained but mud filtrate invasion. Resistivity, or R, is of the adjacent shell formation. Resistivity of the mud, or Rm, and the diameter, gh, of the borehole. Formation water resistivity, Rw from SP. How we can see in this formula, Sw is now our formation equal to R0 divided by RT. That's equal to F multiplied with Rw divided on RT, and this is equal to A multiplied with Rw divided by RT multiplied with Pm. Procedure of this formula. Necessary info is RMF and Rm at a given T, T surf, Td, Bht. Determine formation temperature, Tf, correct Rm and RMF to for Tf, shell baseline Sp, correct Sp to SSP for thin beds, determine RMF RWE ratio, and last one, correct Rv to Rw.
How to identify a zone on the log that is clean, wet, and permeable. Pick the maximum value of SP in that zone. In this formula, we calculate formation T and at the depth of SP BHT, bottom hole temperature MSTE, annual mean surface temperature FD, formation depth TD, total depth of TF, formation temperature. Second formula shows the main information about converting of RMF from surface T to formation temperature. RMF is the RMF at formation temperature. RMF surface is the RMF at measured temperature. T surface measured temperature of RMF. So next one shows the data about finding the equivalent formation water resistivity RWE from the SP and RMF. RWE equivalent RWE. The next one is in the next formula. We should convert RWE to RW.
SP very useful for many aspects of geology, and one of them is shale volume. Shale volume is used in the evaluation of shale sand reservoirs and as a mapping parameter for both sandstone and carbonate facies analysis. Here you can see formula for calculation of this volume. V shale is equal to 1.0 minus PSP divided by SSP, or you can use V shale that's equal PSP minus SSP divided by SP shale minus SSP. Principal uses of as SP log. Let's some of knowledge that we take from this video. First of all, SP log used for resistivity of water, volume shale. SP log used as permeability indicator for founding phases and as correlation. For resistivity of water, we need use RMF and T. For volume of shale SSP and shale baseline, for permeability indicator shale baseline, and for phases clay grain size relationships.
Thank you for attention.